You working?
I can't get out my bed right
I
now.
think we're working.
I hurt to come on my bed.
Yeah? Alright, there we go. Huh.
It hurts though.
It'd be really unfortunate if I did. I have a full day.
Alrighty. Well, I will begin. Excuse me. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this time we have to meet together and to study your creation. Just pray you to again guide our thoughts and just help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so let me get going here. Is there any question about anything? I should mention one thing before I forget. Problem 64 in the homework. Problem 64. You can omit part A because something unfortunate happened with that problem. So like typically with the bounded monotonic sequence, the trick we used was to take the limit of the recurrence relation, and then it gave us some like non-trivial formula for the limit. That example is rather annoying in that when you take the limit of the recursion relation, you get L equals L, which is true, but useless. So yeah, 64 part A you can omit. Now part B is actually pretty simple. You just have to sit and fiddle with it. The formula for A sub n in that problem is actually pretty easy to derive. So once you see that, you'll realize that it's actually a very simple problem with that in mind. So that's all about that. Any other questions about the homework before I get into the new stuff?
Yeah. So like question like 61, like the first one, like how are we treating these as functions and just like finding the limits of them, or
61, the first one?
Or just like all of them? Like are we treating them as functions and finding the limit? Like how do we start that?
Yeah, we treat them as functions, find the limits. You can use the theorems I talked about, right? Like, let me just grab yours for a second. Now you won't know what I'm talking about. But so like yeah, part A, algebra. Part B, it's the composition of a function with an expression. Your expression's going to infinity. What's inverse tangent of infinity? Pi over 2. Oh, okay, good. You did that problem. Part B. Part C, you've got 3 to the n times 4 to the minus n plus 42. What's that? That's 3 over 4 to the n plus 42. What's that limit to? What's 3/4 to the n go to? Goes to 0. So the answer is 42. Part D, you can just basically do algebra part D. What's minus 1 to the n over n limit to? Minus 1 to the n over n. This goes to 0, right? But yeah, pretty much just study the formulas. There's not like a detail. A lot of these you can just write down the answer. Some of them, let me say here, I think part A, part like A, C, and G, I'd like to see, maybe D as well, I'd like to see like one algebra step before you write the answer down, but there's not a lot of work that needs to be shown for these. Gotcha. So I think the answer to your question, yeah, they pretty much think of them as functions, process their limit, but yeah.
What about like 67 and 66 and like all those?
Oh yeah, we're not to those yet.
Okay.
Yep. Okay, so let's talk about finite sums. So we're going to talk about series, but just as a warm-up for that, I should talk to you a little bit about the finite sum notation. And so, I don't know if you've ever thought about this or not, but how would you actually define, let's say, the sum, I don't know, k equals n naught to n of a sub k. All right, so this would be, you start at n naught, and then you say n naught plus 1, and then you just keep going, right? You keep going and going until you get to what? Till you get to a sub n. So this is summation notation, right? Now a lot of times the n sub naught will be 0 or it'll be 1, but I'm trying to write notes with an n sub naught there to reflect the fact that we could start at 0, we could start at 1, we could start at 10, like you got choices. You could start at minus 5, you know? You could have a finite sum that starts with your index being minus 5, that'd be fine. How do you actually define this though? Here's how we define it. So the sum, k equals, let's say, n naught to n of a sub k is equal to, well, it is equal to a sub n plus the sum k equals n naught to n minus 1. And the sum k equals n naught to n naught, well, that's just equal to a sub n naught. Now, I think maybe in the notes I had the good sense to put n sub 0 equal to 1. So if you'd like, you could make n sub 0 equal to 1, and maybe this would be less weird. I probably should have done that. My bad. But anyway, my point to you is just this. We can define a finite sum recursively. Now, for a long time, it didn't even occur to me to ask a question here. I just accepted this as something that makes sense, right? And it's fine. But understand that if you want to be careful about it, that is defined recursively. The sum from one thing to itself is just the first thing. And then to get like past that, you just keep adding one to the last one. And that defines finite sum. All right, so properties. Props. So if we've got AK plus some BK, it's equal to, guess what? The sum of AK plus BK. And if you've got a constant times the summation, guess what? You can bring the constant inside. So these are properties of the finite sum, all right? And if I don't care about where it starts, I just omit the starting point for the index, right? I mean, this is so this is like an abbreviated notion. This is an abbreviated notation for the finite sum. See the difference? Here I didn't write the starting and the ending point, right? So this kind of notation for finite sum is okay in as much as the starting and ending point don't matter. Now, if the starting and ending point of the finite sum are like the whole point of what you're doing, well, you better write the starting and the ending point for the index, right? For example, here's a theorem. Do you guys know? Well, here's an easy one. If we do sum k equals 1 to n of 1, what would that be? What if we added k? What if we added k equals 1 to n of k squared? What would you get? The first one, I think everybody can kind of just intuitively figure out. So what we're doing here is we're adding 1 to itself how many times? N times, right? So what's that equal to? N-fold copies, right? What's the formula here? N, yeah, right. What if you add, n to itself? Well, what if you do 1 plus 2 plus 3 plus da-da-da-da plus n? What's that equal to? N factorial is not correct, but nice guess. Smaller than that. So like, famous story, Gauss, when he was like a kindergartner, the teacher, gave them, he said, I tried to waste the time of the students, said, add up the numbers from 1 to 100, right? And they used to work on these like slate boards or whatever when they're, back in the one-room schoolhouse and all that. Actually, I'm not sure he was in a one-room schoolhouse, but anyway, he probably had a slate. And like as quick as the teacher asked it, he said 5,050, I think it is. It's like, wait, what? How did you add the numbers from 1 to 100 so quickly? Well, the thing is, Gauss as a child understood that there's a formula. Like that. Try it out. Add the numbers from 1 to 10. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. What do you get? 55? Did you actually add the numbers, or are you just using the formula? So, let's see here. 10 plus 9 is 19, plus 8, 20. Oh man, this is not good for me. What's that? 27. Then we add what? 7, 34, add 6, 40, add 5, 45, add 4, 49, add 3, 52, add 2, 54, add 1, 55. It works, right? In the case n equals 10, that's a proof, right? That is not true, right? But you can prove this formula by what's called mathematical induction, all right? So assume it's true for n. You can show it's true for n plus 1 by some algebra. I think a lot of you take Math 250, So you'll see that kind of proof technique there in more detail. I mention it here because we need it at times. The formula for the sum of k squared is not at all obvious, but this was also known to Gauss. So these are known as Gauss's formulas because, well, Gauss knew them. Gauss was a 18th to 19th century German mathematician, one of the last people to really have a mastery of all of mathematics that was known at the time, and then some. Also kind of a jerk, apparently. But anyway, his habit of, like, anytime somebody come up with something new, he'd be like, oh yeah, I did that. Like 20 years ago, I just didn't publish it. It's like, did you though? But yeah, I don't know. People can debate. Anyway, so these are Gauss's formulas. So here, you know, those are pretty non-trivial formulas. We'll use these on occasion, okay? So I just want you to know about them. If we actually want to calculate a Riemann sum, for example, these are super useful. All right. Okay, so I will spare you the proof of those, okay? Now, golly, that's about all I got to say about finite sums. Finite sums have this lovely property that the sum of finite sums is the finite sum of the sum, and you can bring constants in. This is just the distributive property for like a bunch of things. That's all this is, okay? So that brings us to our actual main event for today, which is the definition of infinite series. So let's do that, if I can find my marker. So let's talk about infinite series. So here's the definition. The series, summation, k equals n naught to infinity of a sub k. So it's just like the finite sum I wrote over there, except now we don't stop. It just keeps going and going and going, all right? Has nth partial sum. Now the nth partial sum will be a finite sum. All right, nth partial sum here, k equals n naught to n of a sub k. So unlike the one that keeps going and going and right above, this one stops at a sub n. All right. And then we say the series, which is sum k equals n naught to infinity a sub k, converges or is summable if its sequence of partial sums converges. The limit of the sequence of partial sums is known as the sum of the series. And we write the sum k equals n naught to infinity of a sub k is equal to the limit as n goes to infinity of the sum k equals n naught to n of a sub k. If the series is not convergent, then we say it's divergent. All right? Is divergent. Also, if the limit as n goes to infinity of the nth partial sum is equal to plus or minus infinity, then we write sum k equals n naught to infinity of a sub k is equal to plus or minus infinity. So what I'm saying is, not only do we say that the limit is equal to its limit of partial sums in the context that the limit exists, we also put equality there when the limit's plus or minus infinity. But in those cases, we would say that the limit diverges, because the limit does not exist. When we say it exists, we're talking about as a real number. Yes, sir?
I think it's like the third summation you wrote. Y underneath, is it n equals n naught, not k equals n naught, or is that a k?
They're all k's.
Okay.
You talking about this one?
No,
This one? This one. It's supposed to be a k. Sorry, my k's are degenerating. Now, the k is not sacrosanct, right? Like, you could take this whole definition, and everywhere I've written a k, you could replace it with a j or an m. You know? Yeah.
Is the a sub n of the especially big one that you wrote supposed to be k?
They're all k's. So there's no a sub n anywhere here. These are all k's. It's just my handwriting degenerates down towards the bottom of the board. These are all k's. Thank you for that question. I will try to make my k's more k-like, if that's okay. Let's see here.
I only asked because I thought it was an n.
Yeah, no.
N could equal n naught.
No. These are all k's. The n is fixed in the nth partial sum,
Yeah.
and it's not even appearing manifestly in the series. All right, so this is the full, gory, here's all of our notation definition, right? What's the simple takeaway like, what's the, if you wanted me just to like strip it down, like what's the definition of a series? Briefly, the sum k equals n naught to infinity of a sub k is equal to the limit as n goes to infinity of the sum k equals n naught to n of a sub k. This is the definition of a series. It is the limit of the sequence of partial sums if that sequence exists, if that limit exists. It doesn't have to exist, all right? But if it does, then we say the series converges, or we could also say that it's summable. Now, there exist Calculus 2 teachers who refuse to use the word converges for series because we've used the word converges for sequence, and they don't want students to be confused. I reject this because it's not standard practice, and also because it will put you at odds with like other deeper mathematical literature. So we do use the word converge in different ways for different objects. You have to understand the context of the word, right? If a sequence converges, we're talking about that epsilon n thing, right? For each epsilon greater than 0, there exists a big N such that if the little n is larger than the big N, you can make the absolute value of the difference between the sequence and its limit as small as you like, smaller than epsilon, right? That's the definition of sequential limit. The definition of the series converging is to say that the sequence of partial sums converges, right? So let me just strip off the n naught here for a second and make our life a little bit simpler. So if n naught is equal to 1, as is often the case, we're looking at, the sum k equals 1 to n of a sub k. That would be your nth partial sum, right? What's it look like? a1 plus a2 plus a3 plus plus a sub n, all right? So a lot of times that's what we're up against. What does the sequence of partial sums literally look like if we write it in list notation? The sequence of partial sums looks like this. a1 plus a2, a1 plus a2 plus a3, a1 plus a2 plus a3 plus a4. Well, we could be here all day, right? And so forth, it goes on. This is the sequence of partial sums. It's related to the sequence just formed by a sub n, but it's certainly not the same, right? These are different things. The sequence of partial sums is formed from adding up the terms in the sequence. Okay? So let's see, what else can I say about this? So I will test you on the definition. You need to memorize the definition, at least the brief one. All right? So work on that sooner rather than later, because everything I'm doing past this point won't make a bit of sense if you don't understand the definition. It's central to everything we're doing past this point. All right, so like first example, easy example, example 1. How about this series? What if we look at the sum k equals 1 to infinity of, of 1? What should happen here if we just do 1 plus 1 plus dot 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 dot? What should happen to this one? Can we calculate the nth partial sum? What is the nth partial sum here? K equals 1 to n of 1 is just equal to what? If you don't like my k's, you can start writing them as j's. But let's see here. So what's that? It's n, right? So therefore, the sum k equals 1 to infinity of 1 is equal to the limit as n goes to infinity of what? Of n. Which is infinity, right? So this, your first example here, is a divergent series. This one definitely diverges, right? Okay. Well, another, yeah?
I have a question. What was the sequence of like the A1 and then like the A1? What was that?
This is called the sequence of partial sums.
Okay.
In order for the series to be summable, that sequence must converge. If that sequence doesn't converge, the series is said to diverge. Like my example 1. This is a divergent series. The next most stupid example I could give you, which is really, really simple, what would happen if you just take the sum of 0? You know, like the series formed by just adding 0 together infinitely many times. What happens there? So we're looking at the limit as n goes to infinity of the sum k equals 1 to n of 0, which is you're adding 0 together n times, right? What happens if you add 0 together finitely many times? 0, right? So inside the limit, you're not doing things infinitely many times, right? I mean, you're actually only adding it n times, which n times, n adding 0 up n times, you just get 0, right? It's not something approaching 0. It's just strictly 0 here we're adding, all right? So, well, that's just 0, right? So there you go. So this is, in fact, the sum of this series is 0, right? So this one is, it's convergent, right? This one's convergent, or you could say it's summable, all right? More than that, its sum is 0. Great. So this brings us to our first convergence. Well, actually, this is not a convergence test. What I'm about to show you is, in fact, a divergence test. So all this does is it destroys your hopes and dreams of the sequence of the series you're looking at, in fact, being a convergent series. All right. So here's the theorem, and the theorem is this. This is called the nth term test. Although I guess I might call it the kth term test if you want. I don't know. I'm going to call it the nth term test. It's just kind of in my blood. But k equals n naught 2. This is always a debate I have, guys, about whether or not I should write the series using an n or a k. I've opted for k in the notes this time, but every so often my old preference for n bleeds through. Here's one of them. If the series converges, then the limit as n goes to infinity of a sub n is equal to 0. So a logical corollary to this sentence is the following one, right? If the limit as n goes to infinity of a sub n is not equal to 0, what's that tell us then? Then the series diverges. Notice that this, the so-called nth term test for divergence, I'm calling it the nth term test. I'm explicitly calling it the nth term test for divergence because it will only certify divergence. All right? I will soon show you examples of sequences, series rather, where the terms go to 0 and yet the sum diverges. Like it doesn't, series does not diverge, does not converge. Okay, so here's the proof. So let's suppose that the sum k equals n naught to n of a sub k limits to L as n goes to infinity, right? That is to say, suppose that the series converges, right? To say the series converges is to say that the sequence of partial sums converges. That's what I'm saying, all right? Now here's a trick. How can you find me, and let's call this thing, well, maybe it's a good a time as any. Sometimes, you guys, it's helpful to have a shorthand for the nth partial sum because it gets awful. It gets old writing all of this, right? So if we want a shorthand, a lot of times I use like this s sub n for the nth partial sum, if I don't want to write the summation notation for an argument. So check this out. What is s sub n minus s sub n minus 1? What's that equal to? Let me write it out. So you're looking at, you know, the sum. Well, let me write it out this way. Yeah. So sum k equals n naught to n. Is that in this room or out of this room? I can't. Man, there was a genuine ruckus in my office. I don't know, like there were girls shouting in the hallway or something. I felt like I was at the Sheets or something. I don't know, like it was. My wife takes the kids to Sheets for like slushies or ices or whatever. And one of the times they were there was this like person acting up, and like the register lady just like, get gone, get out of here, get gone. There's kids in here. They start swearing and stuff. So she just like booted them from the store. It's awesome. But there's a fist fight at that Sheets on 29 like every week or something. I don't know. Anyway. Listen, so I just defined for you guys a minute ago, what's this mean? Recursive definition, right? This is a sub n plus the sum, what? K equals n naught to n minus 1, right? Of a sub k. So of course you could also see this in the plus dot 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 notation if you want, and that's fine if you want to do that. But the larger point here is that if you take the difference of the nth and the n minus 1th partial sum, all that's left is a sub n. Right? Okay, so apparently if we want to calculate the formula for the term, the nth term, we can just take the difference in the nth and the n minus 1th partial sums. That's kind of a neat observation. Okay? Okay, so then what? What's the rest of the proof? There's really not much more to do. Yep.
Where did the a sub n come from? Like, what is that? Like, where did you get, like...
Oh, this is the definition of finite sum. We defined the finite sum recursively. This is equal to that. How do you get to the nth one? You take the n minus 1th sum and then you add a sub n. That's how we built up the finite sum. If you want, I could, listen guys, here, let me make it less weird. So you could do like this, right? a1 plus a2 plus da 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 plus a sub n minus what? a1 plus a2 plus da 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 plus a sub n minus 1, right? And if I wrote it like that, you guys wouldn't even flinch. You'd just be like, oh. Well, when you take the difference, of course, that's all that's left. And that's all that's happening here. I'm taking the nth partial sum minus the n minus 1th partial sum. Right? I'm just inconveniencing myself to start at n naught for the sake of, yep.
For this notation, could you actually take the difference of both summations at the top? So it would be like n minus n plus 1 kn naught to the summation from k equals n naught to n minus n plus 1 of a sub k.
Well, I think that's what I did. I mean, I'm saying that this
I'm saying
breaks, I'm saying that
legal to do in the notation.
this right here, I mean, that's the definition of the finite sum. I think that's what you're saying to do.
Yeah, kind of. I'm just
Yeah.
taking the two different forms since they both have the same variable on the side, and then putting them into one summation with the top being added, but in this case subtracted together.
Oh, if you're saying we could also combine these sums because they've got the same range, that's also true. You could do that, but then you'd have the sum of 0. I mean, either you can just say, look, these are the same, they cancel, right? Yes, you could also, I think what you're saying, if I'm reading you, right, what you're saying is I could take these two things and I could rewrite it as k equals n naught of a sub k minus a sub k. I can do that. The reason I can do that is because it's got the same index structure, if you will. That's true. This would be 0, yeah? So you add 0 together finitely many times, you still get 0.
Kind of. I was just saying taking the notation and putting n minus n plus 1 on the top of that
And
summation.
putting n minus n plus 1, n equals to n minus n plus 1.
No, not n equals n minus n plus 1, but because you're subtracting the two different
Yeah, I don't,
summations.
well, I don't think we disagree. But so anyway, the punchline here, though, is what? What happens is the limit as n goes to infinity. What happens? So as n goes to infinity, what do we get? No.
0?
We get the limit, yes, we get 0 because we've got the limit as n goes to infinity of s sub n, right? Minus s sub n minus 1. And both of these go to what? L and L by assumption, right? L minus L, also known as 0. See, because we're assuming that the limit of Sn goes to L. That is the assumption that the series converges. Okay, so that's the nth term test for divergence. And of course, you could also write it, you could take the limit as k goes to, you could take the limit as k goes to infinity of a sub k if you wanted. It wouldn't be, any different logically, okay? So, let's move on here. So example, yes, sir.
But does it s sub n minus s sub n minus 1 is equal to a to n?
Yes, that's true. That's what I said.
So how would that equal 0? Or is
The limit is 0. I didn't say it's equal to 0.
Okay.
The limit of this is 0. Uh-huh. So example, where am I? 1, 2, 3. Example 3. Here's a simple one that's a little bit interesting. Consider, what if you got inverse tangent of 1 plus inverse tangent of 2 plus dot, 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 right? Observe A sub n, we could say, is equal to what? It looks like it's going to be equal to inverse tangent of n, right? Bless you. So if I recognize this as a series starting at 1, right? You could rewrite this infinite thing as the sum k. I mean, you could use n. You don't have to use k. I'm going to use n for a second here. N equals 1 to infinity of inverse tangent of n. I could do that, yeah? I'm mostly trying to reserve n for the partial sum. That's why I'm sticking mostly with sums over k. But you could use n there. It's also fine. But my point to you guys is that this is equal to k equals 1 to infinity of inverse. Like, there's no necessarily fixed independent meaning of n or k. These are indexes of summation. It's, you know, those are used up in the process of the series, the summation of the series. Just like if you have integral from x to, you know, integral over integral of f of t dt from 1 to 2, there's no t in the answer, right? It's a number. Like, I could take integral from, you know, in the same way, integral from 1 to 2 of f of t dt, it's equal to the integral from 1 to 2 of f of x dx, right? There's no x, so there's no t in those answers. The variable is a variable of integration. It's just a device to express this summation. Well, this continuous sum for the integral, or this discrete sum for the series. Like, there's no independent, separate meaning of k and n. Which isn't to say they don't have meaning, of course, because, well, we're talking about their meaning today, right? But what I'm saying is you can change the letter. All right, anyway, so let me erase that. Stop answering questions you're not asking. So how about this? What's the limit as n goes to infinity here? This is what? Not 0. This is pi over 2, which is, by the way, not equal to 0, right? So thus, you know, inverse tangent of 1 plus inverse tangent of 2 plus dot, 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 dot diverges by the nth term test. End of story. Now, I should make a point here before we go on. And this is a point I can't justify yet because it requires something we're not doing today, probably. But it should be mentioned, it should be emphasized that the nth term test does not go both ways. All right, like in the following sense. Yeah.
So it diverges because pi over 2 is pi is technically infinite.
No, pi over 2, pi is like 3.1415 blah blah blah. That's like,
So it goes on forever.
well, sure, but it's a number. You know, I mean, and pi over 2 is like 1.57. Anyway, the point is it's a number. It's not equal to 0, so therefore it diverges. So example 4, you might be, here's the one of the fundamental temptations of calculus 2 is to think about this one. Sum k equals 1 to infinity of 1 over k. All right. So this is equal to what? 1 plus a half plus a third plus a fourth, so forth and so on, forever and ever, right? What happens if you try to do the kth term test here? What's the limit of k going to infinity of 1 over k? That's 0, right? Right? And this implies nothing. This implies nothing. Well, that's too strong, actually. What that implies, I could cross out nothing. It implies there's still hope. Maybe it could possibly converge. But the bad news is it doesn't. This one does not converge. Yep.
So the only purpose of this test is to develop a divergence.
Yep. That's why I'm calling it the divergence test. So this, as it turns out, this is called the harmonic series, and we'll prove it doesn't converge in a future lecture probably. So this is actually called the p=1 series in terms of our later language. All right, so let's move on here. So then the question becomes, you know, are there any series you can calculate the sum of that aren't as stupid as as just adding 0 together infinitely many times, right? Like, is there any hope that we can actually calculate the sum of the series explicitly? And there are a few examples where I can actually straight up calculate the sum of the series. I pretty much only know of 4 ways. 4 ways. 3 of which are accessible to us at the moment, and I include in the notes. All right. The first I would call a telescoping series. So this is example 5. Example 5. You could have what's called a telescoping series. Something like, let's see here, k equals 1 to infinity of 4 over 4k minus 3 times 4k plus 1. Now that doesn't necessarily look like a telescoping series on its, like, it's not manifestly so. We need to do some kind of pre-processing here, all right? And so, well, first of all, the first thing you usually try for any series, just it's sort of opening the triage, if you will, for the series as you're treating your patients. You look at it, you go, nth term test, or in this case, kth term test. What happens? As k goes to infinity, that goes to 0. Okay, maybe it doesn't diverge. Maybe. All right? And then the next thing is, well, the next thing is complicated. There's a lot of things. It's going to take me about a week to tell you the next thing. But this one here, we can set this equal to a over 4k minus 3 plus b over 4k plus 1. Right? So we can do partial fractions on this expression. And when you do that, it works out to 1 over 4k minus 3 minus 1 over 4k plus 1. I won't show you the details, but you can easily figure those details out, right? Partial fractions. And so, apparently what we're up against here, if we want to calculate the nth partial sum, right? We could look at sum k equals 1 to n of, as it turns out, 1 over 4k minus 3 minus 1 over 4k plus 1. All right, so how does that go? So, all right, whenever you're looking at a series and you find the nth partial sum has got like a difference of kind of the same sort of formula shifted a little bit, that might be a telescoping series. So the way to understand it is to like just write it out and see how the cancellation happens. That's why it's called telescoping. So if you start writing these things out, what you got? Plug in k equal to 1, what do you get? 4 minus 1 is, 4 minus 3 is 1, right? So I get 1 for the first term. What's this one? Put in 1, I get 5, right? So minus 1/5. So I'll put parentheses around this. This is the k equals 1 term. How about k equals 2? K equals 2. I get 8 minus 3, which is 5. So I get 1/5. What comes next? K equals 2. 2 times 4 is 8. 8 plus 1 is 9. Minus 1/9. What happens next? Well, k equals 3. So 4 times 3 is 12. 12 minus 3 is 9. Let's see here. K equals 3. 12 plus 1 is 13. So minus 1/13. And this keeps going, right? Keeps going. As you can see, though, and let me just put some labels here. This was my k equals 1. This is from k equals 2. This is from k equals 3. I'm going to start us over here at k equals n minus 2. Then I'll do k equals n minus 1. Then I'll do k equals n. That's more than I need, but I just want to make sure we understand the pattern. You should be aware. This one's pretty simple. There's not a lot left over at the end. Sometimes you have more left over at the end, so you have to keep more of the beginning and the ending to see the cancellation properly. So I'm doing a little bit more than I need to here. If you put k equals n minus 2 into here, what do you get? Four times, well, I'll just write it out. 4 times n minus 2 minus 3, right? Minus 1 over, let's see here, 4 times, you know what, let me save myself some writing here, guys, and just do some of the pre-processing up here. What is 4 times n minus 2 minus 3 equal to? Four n minus 8 minus 11. And then minus what? 1 over, what's 4 times n minus 2 plus 1? 4n minus 7. All right. And then the next term is 1 over 4n minus 7 minus 1 over 4n minus 3, I think. You can see the pattern here. And then 1 over 4n minus 3 plus 1 over 4n plus 1. That was a minus, my bad. And my labeling obviously has gotten, that was very, very overly optimistic on my part in terms of my choice of font size and how big those expressions would be. So here's your k equals n minus 1. Here's the nth term. All right. Very good. Now what? Now we do the telescoping, right? So like this. Chuck, 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 chuck. You gotta use your imagination. It's over here. Oh, all that's left is this guy and the starting one. So all that's left from all that is 1 minus 1 over 4n plus 1, right? What's the limit as n goes to infinity? So this goes to 1 as n goes to infinity, right? Therefore, the sum 4 over, see at this point I start labeling this series, I give it a name, but I'll write it out again for you guys since I like you guys. 4k plus 1, at least I like some of you at least. Let's see here, k equals 1, no I like all of you, what am I talking about? That's nonsense. Let's see here. 1 minus 1 over, so this is the nth partial sum. We found a formula for it, and this is equal to 1. So therefore, not only do we get to say that this series converges, it converges, its sum is in fact equal to 1. Actually being able to explicitly calculate the nth partial sum and take its limit like this is a precious and rare event. Usually we can't do it. Usually we can't do it. So the other kind of example that's like super important, so I guess I'll do it on the middle board here, is the geometric series. So geometric series are also series which, oh man, the geometric series is another one that we can actually explicitly calculate the limit of. So you remember we talked about the geometric sequence before, right? So the geometric series is just when you add up the terms in the geometric sequence. All right? I think well, you guys know the definition now. You've already memorized it, so we're good, right? Do, 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 do. So I guess I should probably make a definition. This one's kind of important because we need to recognize this when we come up against it. Definition, let C and R be real numbers, then find a marker that's not stupid. I'll leave this thing in here. Junk. All right, then the sum k equals 0 to infinity of c r to the power k, which is explicitly c plus cr plus cr squared plus dot 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 is a geometric series. All right, so this is the geometric series. So let's calculate. What's the nth partial sum for the geometric series? Say sum k equals 0 to n of cr to the k. What do you got there? You got your c plus cr plus cr squared plus dot 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 plus c r to the n minus 1 plus cr to the n. All right? So I'm showing you at the moment a standard trick. It was shown to me. I've shown the generation before me. Everyone's seen this. All right? So what you do is you take the geometric series partial sum, right, and just multiply by r. So what is r times Sn? Well, it's cr plus cr squared, right? Plus cr cubed plus dot 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 plus cr to the n plus cr to the n plus 1. Did you guys get it? It's just multiplying the line above by r. It adds a power to each exponent, right? Now, even though this is in some sense not a telescoping series, all right? There's a famous calculus book by a guy named Apostle who claims every convergent series is telescoping. But I mean, that may be in some technical sense true. But this does not, on its face, this does not look telescoping, right? Okay. But you see what happens when we take the difference of, what happens when we subtract Sn and Rsn? What do you get? There's not many things that I ask you to prove in here, but this is one of them that I've put on many a Calculus 2 test. Prove the geometric series result. That's what I'm doing right now. What's that? C? C, and then what? Minus what? Oh, you factored the C out. Cool. But I'll just leave it like that for the moment. But yeah. So you guys you're recognizing this cancels this cancels that, right? All the way on out until this cancels, right? The only thing that's left in this difference is this guy and that guy, right? And, well, if we could find a formula for the nth partial sum, it would be lovely, right? Can we? Yeah? What's the question?
Are you saying that is a telescoping series, or are you saying it's
I don't think it's a telescoping series on its... What?
Why do you not think that?
Because it's not telescoping. I mean... When I think telescoping series, you can write the formula for it as a difference of the same kind of pattern repeated. So, I mean, what we just did here is reminiscent of the telescoping series for sure. Yeah, absolutely. This is, well, C times 1 minus r to the n plus 1, right? Factor the C out, and then solve for Sn. What do you got? The constant, right? times 1 minus r to the n plus 1 divided by 1 minus r. Whoa, so there's a formula. There's a stone cold formula for adding together the first n terms in a geometric series. You can use this formula if you come across a geometric series that you want to truncate. If you have a truncated geometric series and you want an explicit formula for the first 100 terms, you can use this, right? Like, for example, application. If I wanted to add 1 plus a half plus a fourth plus da-da-da plus, 1 over 1,024, 24? 1,012, right? What is this? Or is it 24? I can't remember. 24. So that's what? 1 over 2 to the 10th, right? If I remember right. What's that equal to? So C equals to 1, R equals to 1/2, N equals to apparently 10. If I remember my stupid binary trivia right. So you got what? You got 1 minus 1 over 1,024, I think. Oh, wait a minute, n plus 1. So I need what? 2,048 divided by 1 minus a half, yeah? So there you go. It's apparently 2 minus 1 over 1,024. There you go. There's the sum of the first 10 powers of 2 in 20 seconds. That's not bad. When the robots gain consciousness, this will help us. I don't really believe in that. Do you believe robots can gain consciousness? I don't believe it. I don't think it makes sense. They don't have a soul. Yeah.
Resembles consciousness, but wouldn't be the same thing.
Yeah. If you think about it, it seems like the more we use computers, the less soul we have. It's kind of absurd to assume something that's just a computer would have soul, isn't it? But anyway, I digress. Okay, so what is the limit as n goes to infinity of this thing? Continuing. What is the limit as n goes to infinity of this nth partial sum? I could have made a mistake too. How about this? If we studied this limit, right? The limit of r to a power, how does it go? If you take the limit as r goes to infinity of a real number r, what was the story? It only converges when? When the absolute value of r is less than 1. Otherwise, that r to the n plus 1 term blows up. This we proved. So this is equal to c over 1 minus r if and only if the absolute value of r is less than 1. Sorry, I just used an abbreviation. That is if and only if. That's what that means. In other words, to put it more plain English, the geometric series converges only when the radius of the series, the r, has magnitude less than 1. Otherwise, it diverges. How does it diverge, by the way? Well, because the nth partial sum blows up. Another way you could see it, though, if the absolute value of the radius is larger than 1, this will fall to the nth term test. If the absolute value of r is greater than 1, if you take the kth term, and you take the limit as k goes to infinity, you don't get 0. You get something which either doesn't exist or blows up to infinity. That's certainly not 0. So outside of that case, it diverges by the kth term test as well. So, yes, sir?
Interestingly enough, wouldn't that diverge to negative infinity?